Welcome to Technian's Faculty of Electrical and Computer Engineering, where the world of micro and nanotechnology is advancing, one atom at a time. At the heart of microelectronics lies the search for new materials. Professor Lior Kornblum is exploring innovative alternatives to silicon, pushing the boundaries of what chips can achieve.
One of the key challenges today in microelectronics and the chip industry is to pack more and more logic building blocks or transistors into the chip, into a small piece of silicon. And to do that, we need to make them smaller and smaller. One of the key strategies to continue driving the technology forward is to introduce novel materials to replace or to complement silicon. My group, the Oxide Electronics Lab, harnesses for this task unusual and exotic oxide materials that have surprising, unconventional electronic and magnetic behaviors. And to mature these materials and these technologies towards new chips and new microelectronics, we study the fundamental properties, how the electrons interact with the atoms and with other electrons, and we try to take these new behaviors and craft new devices out of them. We have a very unique infrastructure that is one of a kind in the Middle East, and only a handful of them exist in the world. This is to synthesize novel materials. And the way we do that is by placing a layer of atoms on a layer of atoms, and we can interchange the different atoms, and we can place them on the surface and arrange them into new forms of matter that did not exist on Earth before. We want to have intelligent design of these materials to address specific electrical and magnetic behaviors that are necessary for the next generation of chips technology and microelectronics.
Optimizing materials is only part of the challenge. Professor Eilam Yalon is working to reduce energy consumption and boost speed using ferroelectric memories and novel nanoelectronic devices.
One of the most pressing challenges in electronics today is energy consumption. A key bottleneck lies in the separation between computation and storage. The data transfer between processor and memory units consumes significant energy and time. The research community tackles this challenge by combining memory and logic functionalities together at various levels, and my group focuses at the device level. One of the most promising technologies in that area is ferroelectric memories that enable low power, high speed, reliable data storage. My group achieved a major milestone in this field, demonstrating sub-nanosecond switching of ferroelectric devices. We are now building on this achievement to study the dynamics of scaled ferroelectric devices with high temporal resolution. We have a unique setup that allows probing with below 100 picosecond timescale, which allows us to understand the fundamental limitations of ferroelectric devices and propose solutions to overcome them. We are targeting to pave the way towards more energy-efficient memory technology that meets the demands of future electronics.
Just across the hall, Professor Yuval Yaish and his team harness the potential of two-dimensional devices to redefine the future of micro and nanoelectronics.
My research area is focused on low-dimensional electronics. We know that as the amount of transistor increases more and more, we encounter a problem of density and power and heating, etc. And the main obstacle arises from the fact that the transistors or the computing devices are located on the interface between the silicon and the silicon oxide. In the last 2 decades, a new family of material was discovered. These materials called the two-dimensional van der Waals materials. And practically they define like a new periodic table. People call it the new van der Waals to the periodic table. This new periodic table consists of like 2,000 materials that play the role of 2D electronic paper that we can stack one on top of the other and build a new structures, which is like three-dimensional. We can put these layers not in one on top of the other, but we can also modify the angle. And when we modify the angle, we practically invent new materials, and the idea is to try to invent new type of transistor. Transistor that's based on tunneling. The power consumption can be much lower, and the transition from off to on can be much quicker. In the last few years, we established at the Nano fabrication unit a 2D center in order to fabricate and study these kind of devices. And since we have like 2,000 of such materials, imagine how many devices we can study and invent.
From new materials to revolutionary devices, micro and nano research at Technion's Faculty of Electrical and Computer Engineering is driving the next generation of technology.